Well, today we're getting practice with some new software and we're getting an opportunity to work with some application of exponential and logarithmic equations. Our focus today is going to be working on mathematical modeling. In this situation, we have a population of a city. Notice that the model that they use, y equal ab to the x, looks a lot like your PERT formula. PERT is continuous compound interest. Population growth is continuous, it's constantly growing, so ultimately this 0.055 represents the rate of growth as a percentage. So that's saying it's growing at 5.5% per year, and your initial value, your principal, so to speak, is the 95,300. So that basically means at t equals 0 in 1996, we had an initial population of 95,300. They want to know, where did the population reach 150,000. So I'm going to do a quick substitution to find 150,000 is equal to 95,300 times e to the 0.055 t power. Now, first thing I'm going to do is I'm going to underline my base. My base is e, so I'm going to divide to get e to the base by itself. So I'm going to have 150,000 over 95,300 equals e to the 0.055 t power. Now, I'm going to do some canceling. Cancel out a couple zeros. That's like dividing by 100. So I basically, 1500 over 953 equals e to the 0.055t. I'm going to change this to logs to find ln of 100 or 1500 over 953 is equal to 0.055 t power. At this stage, we're solving for t, so focus on that side. I'm going to divide by 0.055 on both sides. And then I'll ask that you grab your calculator to find the approximate value. In this case, I believe it's about 8.2 years. Take a second to verify that. If I'm wrong, I'm not here, so I guess it doesn't matter anyway. But you should find, I believe it's about 8.2 years if I recall. Okay, in our next situation, we're dealing with flies, growth of fruit flies. And if you ever get an apple that's set out on the counter for very long, fruit flies start to gather in the spring. They are bad business. The model they asked us to use is a basic exponential growth model. Your final answer might look something like this: y equal 2 times 3 to the x, where 2 represents the initial value, kind of like your principal. 3 is your multiplier, so this would be like tripling each day, which is a little scary. Hopefully that's not the case. Now, 2 would be the initial value at 0 days. We don't know that for sure, so I do know basically ordered pairs. 2, 125 for your xy, and 4 yields 350 for an xy value. So I'm going to use those to allow me to get my values for a and b. So I'm going to fill in my x and y to create an equation. So 125 equals a times b squared, where x is 2. I have two variables, so I need a second equation. So I'm going to say 350 equals ab to the 4th, where x is 4, y is 250. I'm going to do a quick solving in this case for a, because it's simple. A is 125 over b squared. I'm going to substitute that in to find 350 equals 125 over b squared times b to the 4th. Think of that as b to the 4th over 1. And I'm going to do a little reducing to find 125b squared equals 350. Divide both sides by 125 equals b squared. Square root of that, I don't need to do a plus or minus because it would make sense to have a negative growth rate. So my b is the square root of 350 over 125, and if you run that through your calculator, I believe you'll get about 1.673. Now that's my b value. I'm going to plug that in right up there. To get my a is 125 over roughly 1.673 squared. And if you run that through, I'm going to round the nearest whole number. This represents the number of flies. It's about 45 flies for A. So ultimately, my model is f of x equals 45, the initial number of flies, times 1.673 to the x. So this is the initial number of flies, and 1.673 represents 67.3% growth per day, which is a scary amount of growth for flies. The next thing we're going to do is we're going to address from the same problem how many flies there will be after 6 days. So taking my model, I can find f of 6 to be 45 roughly times 1.673 to the 6th power. I can run that through my calculator to find the approximate value. So take just a moment to do so. So that gives me approximately 987 flies after 6 days. Okay, finally it says how many days it will be before there are 1,000,000 flies. Now that just is crazy. I can't imagine what 1,000,000 flies would be like. But if we take our model, fill in 1,000,000, 6 zeros, 45, initial number of flies, at 67.3% growth, we can solve for our exponent. So my base underlined is 1.673, so I need to divide both sides by 45 to get rid of that. Okay, so I will have 1.673 to the x equals 1,000,000 divided by 45. I have an exponential equation. I'm down to base and exponent, so I personally am going to take the log of both sides. That allows me to pull the x down in front. So x will equal, take log of the original divided by the log of the base, 1.673. So if you run that through your calculator, take a moment to do so, see what you end up with. Okay, I really hope you did the math, because according to my calculations, it's a little over 19 days. Scary. So, do the math, make sure that I had that right. Scary numbers. The next and last situation we're going to look at is a half-life problem. Half-life literally means that in this particular case, this isotope, after 5,715 years, half of it disappears. 5,700 years later, half of it disappears again, and it continues. So you start with 6 grams. So my model looks like this. F of x equals the initial value, 6. I'm taking it times 1/2 every 5,700 years. Well, if I put in x here, that means every 1 year it would cut in half. I want to slow down, so I either need to subtract or divide. So I'm going to find that by dividing by 5,715 in the exponent, it slows it down to where every 5,715 years the exponent goes up by 1. So there's my model. I'm going to use it to determine how much will be remaining after 1,000 years. So 1,000 represents my time, so I'm basically going to find f of 1,000. And I have 6 times 1/2 to the power of 1,000 divided by 5,715. And then this question looks kind of like a quiz question that we had on our last quiz. Take a minute, enter that in your calculator, see what you find. Okay, so I come up with about 5.31 grams left over. Do a little estimation. 5,715 years, it should cut in half down to 3 grams. So 1,000 years, we're about 20% of the way through. We should have reduced just slightly. Keep in mind it's multiplicative, so it's not an easy number to estimate, but we can get a pretty good feel to see if that's reasonable or not. From this point on, you're going to be hopefully working with some different types of application problems. Keep in mind we can't give an example for every type. You're going to have to jump in and apply the skills you've learned from exponents and logs to address some new application problems. Have a great day.